Hi, I'm going to try and summarize everything you'll need to know to build networks or applications using LoRa modems. First, I want to go over some terminology and definitions. So, LoRa uses frequency modulation and data is represented as a chirp. A chirp is a signal whereby the frequency either increases or decreases. To generate symbols or chirps, the modem modulates the phase of an oscillator. The number of times per second that the modem adjusts the phase is called the chirp rate and defines the modulation bandwidth. Basic chirps are simply a ramp up from frequency min to frequency max, or frequency max to frequency min down chirps. Data carrying chirps are chirps that are cyclically shifted, and this cyclical shift carries the information. The spreading factor defines the number of bits that can be encoded by a symbol. The higher the spreading factor value, the more chirps used to represent a symbol. The bandwidth is the frequency between frequency min and frequency max over which a chirp symbol is modulated. The modem employs cyclic error coding to perform forward error detection and correction. Forward error correction is particularly efficient in improving the reliability of the link in the presence of interference. RSSI, the received signal strength indication, is the received signal power in milliwatts and is measured in decibels. SNR, or signal to noise ratio. Signal to noise ratio is the ratio between the received power signal and the noise floor power level. The packet frequency error is the offset error between the receiver center frequency and the center frequency of the broadcast chirp. Okay, so now I'm going to have a look at the chipset for the LoRa modems. So this is the company's website that makes the chip. If we nose around here, we will eventually come to the documentation. The modem I have is SX1278. So now we can find out a bit more specific information. Here we've got table 13, which gives us more information about the spreading factors and what that equates to. So here we've got the spreading factor chips per symbol, and then we've got the signal to noise ratios. So table 14, we've got the cyclic coding overhead, and that gives us more information about the coding rate values. So if we've got potential interference, we may want a high coding rate, which then produces a high overhead. And then we've got a table of the bandwidth options. Now the jurisdiction you're in will probably specify which bandwidths are applicable. If we keep going through the document, we eventually come to packet structure, which comprises of a preamble, an optional header, and the data payload. So the preamble lets the receiver sync to the broadcaster. By default, that is configured to 12 symbols. Then we've got an optional header, which specifies the payload length in bytes, the forward error correction code rate, and the presence of an optional 16-bit CRC for the payload. So once we get to the I/O and the pin mappings, we can learn how to actually work with the device. So DIO 0 indicates ready state, and then we have communication on the SPI interface. The second most important bit of information is the register table, which will let us know what all the bytes mean in the various registers. These modems have a setting called a sync word. When the program's sync word is detected, the user can assume that this incoming packet is for the node and can be processed accordingly. So the sync word seems to function a bit like a net mask and lets you isolate out different networks. Figure 33, we have fixed length packet format, and here we've got the preamble, then a sync word, then a optional address byte, the message, and then the CRC. And The sync word for public networks such as LoRaWAN and TTN are hex 34. With that out of the way, we can now move on to configuring and sending and receiving data with the modem. Using an open source library, we can then start interacting with the chip. I added a button to the circuit so that I could switch through functionalities with a button press. Here I've got a register dump, and then if we're curious we can go back to the documentation and we can look at the register table, and this mode that I'm now in is just sending a message periodically. I'm going to now plug in an SDR and try and pick up this message. Here's the packets being decoded. Interestingly, you can granularly set the frequency and bandwidth. So when it comes to networking, as well as the sync word, the base frequency and the bandwidth will be critical for dictating the radio channels which the modems can communicate on. Having looked at the documentation and having used LoRa modems, we can clearly see their limitations. So even though there is the capability for a CRC check, it isn't required, which means the integrity of a received packet is not necessarily guaranteed. Also, there is no mechanism for transporting larger bits of data using packetization, which brings us to LoRaWAN. So what is LoRaWAN? So if we look at the OSI model and then look at the packet, we can see that LoRaWAN makes up for the shortfalls of raw LoRa packets. To learn the ins and outs of the standard, we can go to the LoRa Alliance, and then there's a section for developers. I'm not quite sure how I got there because of modern website design, but here we have documentation. Once we've got the document, it's quite clear that it's a very well thought out standard. So we have a header, a payload, and then a CRC. And then we have the explanation for the various attributes of the header. Moving on, here's a open source LoRaWAN library that implements the standard. So I'm going to write some code and start sending some LoRaWAN packets. I'm now going to switch over to my SDR software to pick up those packets. So here's the received LoRaWAN packet in the SDR software. The received packet, as we can see, is a lot longer and is gibberish. So an extra step is required to decode the LoRaWAN packet and get the payload. For a LoRaWAN server that clients can connect to, there are some brilliant open source projects. ChirpStack is an open source LoRaWAN network server, and this will let you manage the clients that are connecting. Then, building on top of LoRaLAN, the biggest project is Meshtastic. So what this does is provide an API on the application level of the iOS model. And if you go to the GitHub of Meshtastic, we have some protobuf files. Protocol buffers are language neutral, platform neutral, extensible mechanisms for serializing structured data. So this is an example of a good place to start for building an application on top of LoRaLAN. So in conclusion, LoRa provides a versatile radio link that allows data to be transferred between devices. LoRaLAN then builds on top of that to provide a integrity check of data payloads and the packetization of the transmission of larger chunks of data. With a simple application, you could probably just use LoRa in a star topology or a one-to-one. For a more complex networking application, you would then need LoRaWAN.